The first derivative is all about the rates of change. Second derivative is about looking at the rates of change of the rates of change. So we're going to use the second derivative test to find things that are called points of inflection and intervals of concavity, which explore how the rates of change are changing on a function. So what exactly is this second derivative? And of course, this is the derivative of the derivative. It's the derivative of the first derivative. So it's telling you the rate of change of the rate of change of the function. And that's a tough thing to think about. So it's basically saying, how is the slope of the function changing? Is the steepness of the slope, how is it changing? Is the steepness getting lesser or greater? Is the slope beginning to head in a positive or a negative direction? What we find out by looking at the second derivative is, if the second derivative at any point is greater than 0, then the function is concave up at that point. And concave up looks something like this. It's kind of a bowl that holds water. You probably recall that from pre-calculus in Algebra 2. If the second derivative is negative, the function is concave down. Okay, it's kind of the opposite of concave up. And if the second derivative is equal to 0, and the first derivative is not equal to 0 also, the function has what we call an inflection point at that point, meaning that it's changing its concavity from either down to up, as you see here, or in the opposite case, it can be from up to down. So what does that actually tell us? And how do you get that idea? So let's look at how that actually works. Let's look at the concave up example first. And when a function's concave up, that means it's trending towards a positive slope. The slope may start out negative, and indeed it does, but it gets less and less and less negative, eventually reaching 0 and then turning positive. So concave up is an interesting concept. It's more than just an algebraic concept. It tells us that something is beginning to get on the rise. It may not be there yet, but if we look at its slope's getting less and less negative and then eventually positive. So seeing that something's concave up helps us make a prediction that it's eventually going to be on the rise. Concave down is the exact opposite. It means it's trending towards a negative slope. The function may even start out positive with a positive slope, but it's getting less and less positive, and it's heading in that negative direction. It's trending downward. It may not be downward yet, but it's starting to trend downward, and it'll eventually reach 0 and begin to go downward. So concave down, another very important concept. If we can see something is concave down, we know it's eventually going to have that negative slope and begin to lose value. And then an inflection point's a critical idea too, because that place where the second derivative is equal to 0 tells us the function is changing its concavity from either down to up or up to down. And that's an important idea too, that the trend is changing. So let's apply this to a function you've seen before, f of x equals x to the third minus 6x squared plus 9x plus 2. We already took the first derivative of this function before in the first derivative test, and it told us some very important things about the function increasing, then decreasing, then increasing, and having two critical points, a local maximum and local minimum here at x equals 1 and x equals 3. The second derivative test is going to tell us even more about this function. If we take the second derivative of this function, that's the derivative of the derivative, we get 6x minus 12. And we're going to set that equal to 0 to find the points of inflection. So if 0 equals 6x minus 12, move the 12 to the other side, then divide by 6, x equals 2 is going to be the inflection point. And that's this point B that's marked here. So the inflection point is the boundary between concavity. It's going to be concave down or up on one side and the opposite on the other side at that point of inflection or inflection point. And you can kind of see that here. You can see on this function that before x equals 2, this function is concave down. After x equals 2, the function is concave up. So now if we evaluate points on either side of that inflection point, and I chose x equals 0 and x equals 3 just because they're easy to evaluate, we can find out whether the function is concave down or concave up. So we put in a 0 for x into the second derivative. We get 6 times 0 minus 12, or negative 12, meaning that on this side of point B, the function is concave down. And then if we evaluate at x equals 3, put in there, we get 6 times 3 minus 12, that's positive 6. That means the function is concave up on the right-hand side of B. Because if the second derivative is negative, it's concave down. If the second derivative is positive, it's concave up. Now, just to give you another indication of how the second derivative works, I picked a point A on here, on this function, and GeoGebra here can actually show the slope of the tangent line at A. It's that m equals 11.05. So right now at this point A, at slightly less than x equals 0, we have a very strong positive slope. But watch what's happening. The slope's getting lower and lower and lower as we move to the right towards B. It's still positive, but it's getting smaller and smaller. Slope eventually reaches 0, and then it trends negative as we approach B. Now something happens at B, and that's that point of inflection or inflection point. The slope's negative, but it becomes more and more positive. You can look at that m number, and eventually becomes positive, and more so, after point B. That's because the function is concave up along that part of the interval. So that's what the second derivative means. One last thing that the second derivative can do for us, in conjunction with the first derivative, is to determine if a function has a minimum or a maximum. And this is very useful, especially if the second derivative is easy to calculate. Now, if the second derivative is difficult to calculate, like in a quotient rule kind of rational function, you probably don't want to use this. But if it's a polynomial, if it's something that you can take the second derivative of easily, it's actually easier than using the first derivative. And so what happens is, if the second derivative is greater than 0, we know it's concave up. And at the same time, at that point, the slope, the first derivative, is 0, then we have a minimum because it's concave up, and the exact point where the slope is 0 is a local minimum. Conversely, if the second derivative is less than 0, concave down, has a first derivative that's equal to 0, in other words, the slope of the function is 0, and it's concave down, if those two things are happening at the same time, we have a local maximum. And minimums and maximums are crucial ideas because they're where something that we're measuring has reached, at least for the time being, a minimum or a maximum value. So let's put all of this together with an example. F of x equals x to the fourth minus 4x cubed. If we take the first derivative of this, we get f prime of x equals 4x to the third power minus 12x to the second power. We're going to set that equal to 0, and we can factor that. We can take a 4x squared out of both terms, and it becomes 4x squared times the quantity x minus 3. Because of the zero product property, either this first part is 0 or the second part is 0, and if that's the case, both x equals 0 and x equals 3 will make this statement true, meaning that they are both critical numbers. Now let's look at the second derivative. If we take the derivative of the first derivative, we get 12x squared minus 24x, and then we're going to set that equal to 0 to find the points of inflection, or the inflection points. Similarly, we can factor out a 12x out of both terms, and so we have 12x times the quantity x minus 2 equals 0. And by the zero product property, both x equals 0 and x equals 2 make that statement true, meaning that both x equals 0 and x equals 2 are inflection points, places where the concavity is changing. So let's build ourselves a table to figure out what's going on in this function. And we're going to build that table around those two critical numbers at x equals 0 and x equals 3. But thanks to the second derivative test, we're not going to have to choose any points past x equals 3, and you'll see why in a second. We also need to include that inflection point, the extra inflection point at x equals 2 that's not covered. And let's go ahead and get some points in between them. The values of the function at each of those points from -1 to 3 are listed here. When we check the first derivative, when we put the values of x into this function, the first derivative function, we get that this function is decreasing over a large part of this interval. At -1, we have a positive times a negative, first derivative. At 0, of course, it's 0. At +1, we get a positive times a negative, also a negative. At +2, we're going to get the same thing because between these two critical numbers, the slope is not going to change signs. And we don't have to check beyond 3 because of this combination that we talked about earlier. We'll get to that in a second. So before we get to the second derivative, let's look at what the slope does here. So it goes decreasing to constant to decreasing to constant, and we'll find out later that it increases after that because of the second derivative and first derivative test. When we evaluate the second derivative at all these x values, we get positive at -1 because negative times a negative is a positive. Of course, 0 is a point of inflection, and so is 2. At 1, we get a 12 times 1 positive times a negative, so it's a negative value. And then at x equals 3, we get a positive times a positive. It's a positive. It's about the concavity. During the interval x equals -1, it's concave up. In this part of the interval between 0 and 2, it is concave down. And then after x equals 2, it's concave up forever. And because of that, we don't have to check any points past x equals 3 because we know it's got to increase because we have a combination of two things. The second derivative is positive, being that it's concave up, and the first derivative is equal to 0, meaning we have a minimum there. Since it's a minimum, it's got to increase beyond that. We know it without taking the first derivative or doing anything more with points beyond 3. So we have a function that decreases, flattens out, decreases even more, reaches a minimum, and increases after that. Let's take a look at it. And here is that function, x to the 4th minus 4x third, the original function, graphed, and you can see it matches up with what we expect. It is concave up all the way to x equals 0, and you can see kind of half of that concave up bowl. It is concave down from 0 to the next point of inflection, because 0 is a point of inflection, and so is x equals 2. It's concave down from there to there. Then, beginning at x equals 2, it begins that concave up. It's positive second derivative. And the function, as the first derivative showed us, is decreasing, 0, decreasing, 0, and then increasing. So the function does exactly what we believe it to do. So there it is, the second derivative test, which tells us about concavity. How is the slope changing on the function? And putting it together with a first derivative test gives us some powerful tools in exploring and understanding functions.